Okay, let's do the last three questions that I didn't do in the first video. And you'll notice that question one, I'm going to jump to the last question from question one because they're similar. So let's jump down to the very last question. And what I'm going to do is, the first question was a general guidelines or steps for solving problems, and this is specifically for torque problems. And as it points out, if we were in class and if you were taking assignments with a piece of paper and pencil, you would not just be turning in answers like you're doing now, but actually have to carry out these 7-8 steps in completing and showing your work and solving a problem. So the answer to 15 will be shown as I do these other two problems here. And so we're going to start with 13. So here's an apparatus that if we were in class and lab you would have seen. There's a disc that has several discs on top of each other so that we can wind the string around discs of different radii. Here the string is around the outermost one, and that disc is on an axle and it spins around that axle, and screwed in to the disc are these four rods. They're screwed in. This all comes apart, and then you have these these little cylindrical masses that have a hole in them that can be placed anywhere on the rod, and here they're placed so that the end of the mass is flush with the end of the rod, and it's arranged this way. And if you're in lab you would set this up yourself on a stand and you would be able to spin it. And we do a number of lab exercises with this, one where we just let a mass go and it makes the thing accelerate. But in the statics lab we hang a mass here and we hang a mass here, and we want to use torque to figure out how much mass, M2, do I need to place here if I have 200 grams hanging here. How much mass do I need to put here so that when I release it, it's not going to move? In other words, it's in static equilibrium. And so that's a torque problem. And so if we were doing this problem according to the guidelines, the first thing we would do is number problem 13, and if it had parts A, B, and C, we would number those separately so that it would be easier for anyone reading our solution to understand what we were doing. So the first thing is the number. The next thing is the diagram. So we're given the diagram, we don't need to do it. But if we weren't, we would just draw a circle and we would draw the rods and draw the masses so that we created a diagram and label everything. Then the next thing is we do a free body diagram. Well, I've given that to you so you don't have to do it, but you would draw what you see here, and you would just draw it schematically if in fact you were drawing it by hand. And in a free body diagram we put down all the forces. Well, there were only two torques, but there were actually four forces. And so there's the tension in the string pulling on this side, and as long as the mass isn't accelerating, the force is going to be equal to the weight of the mass, m2g. And we hang another string here, and so that's a tension force, but the tension force in the string is going to be equal to the weight of the mass hanging, and so that's m1g. But the apparatus itself has a mass, and so it has a weight, and so the whole thing is falling except it's on the axle. So there's an mg, and that would be, but don't be tricked by the question. It's not the mass of the entire thing, because if we were to draw a schematic of this, you would have a disc. This is the disc and there's the axle, but the axle doesn't turn. It's only the disc that turns. And it turns out the axle has quite a bit of mass, but that's not part of what we're examining. We're examining the apparatus, so the mass of the axle would have to be subtracted. We actually, in one of the labs, we actually have to do that. And so it's not the mass of the whole apparatus, it's the mass of everything else, which is the disc, the 4 rods, and the 4 masses. And that has an mg force, but obviously there's something wrong with this diagram, because this is the force of the hanging weight, this is the force of the hanging weight, and we would, the apparatus itself is going to weigh more than all of those things with the disc and the masses, so this arrow should actually be longer. And since the object isn't accelerating, there has to be a normal force here, and that normal force, this doesn't come up in the problem, but if it did, this normal force, because the sum of the forces in the y direction have to be 0, that's the only up force, right? The weight of the apparatus minus the axle, the weight of the hanging mass of 2, the weight of the hanging mass of 1, all those would have to add up to the normal force. So the normal force would be the sum of all the down forces. So there's our free body diagram. But in the free body diagram, which is drawn for you, you'll recognize that there are 4 forces, but there are only 2 torques. And so we want to physically understand what we're doing. So we see that this torque is going to, if it's not balanced, will twist the apparatus in a counterclockwise direction, which is positive. And this torque is going to tend to rotate the apparatus in a clockwise direction, which is negative. So there's one negative torque and one positive torque, and those 2 torques have to be 0. And so that's how we're going to solve the problem. But there are some other questions to answer before we get there. Let's take a look at those questions. Oh yes, I should have said, you should do the problem as much as you can before you watch the video. I'm going to give you all the answers here, but it's not going to be very instructive for you unless you do it on your own first. So do as much as you can and then come and check the video. And if you, even if you get most of the answers right or all of them right, it might be good to listen to the details of how this problem actually would be done if you would write, if you were writing out the solution for a quiz or an exam. Okay, so we already said that there were 4 forces, and there were 2 torques, one clockwise, one counterclockwise. And the figure on the right, m, refers to the mass of, not, as we said, not the entire mass, the mass of all the parts except the axle. So that's the disc, the 4 rods, and the 4 masses. And the figure R1 is the distance. You can put displacement, but I think the best word is distance. It's the distance from, whoops, that goes here. It's the distance from the axis, or the axle, but axis is a better word. So that R, remember, people call it a radius, but it's not a radius. R in the torque equation, right? Torque equals RF sine theta. That's what we're using. You need the R, the F, and the sine of theta. The R is always not a radius, but a distance from the axis to where the force acts, from the radius. And in this case, so the torque 1 is going to be this distance, R1, which goes from the center of the axle, actually, to the point where the string is hanging, because that's where the force acts. And R2 is measured from the center of the axle, because it's pretty thick, actually, so you measure to the center. And that measures exactly to the point where the string M2 is hanging. Right, so refers to the distance from the axis to the point where the string, because it's the string that's exerting, the mass actually isn't exerting the force, it's the tension force. And in this case, I'm not sure why I asked you to find, usually in the lab what we have to do is find M2, but here I give you M2 and I'm asking you to find what R1 is. So to find R1, we're going to do the general solution following the guidelines, and then we're going to use the general solution to actually calculate the answer for, for this box here. And the general solution is a multiple choice question because you can't really write out equations here, but in an exam or in a written exam or quiz question you would actually have to write all that out. So let's work through that together. Okay, so we've done the diagram and the free body diagram, and now to solve for R2, or R1 I guess it was, we need to do the sum of the torques. So you may think that's the next equation, but in order to do the sum of the torques, step 3 in the steps of the other question, this is actually step 4. This was step 1. This was step 2. Step 3 is identify the axis, and the axis is going to be the axle. And you say, well, what do you mean? The sum of the torques about what? Isn't it obvious? Well, in this case it is obvious. This is going to twist about the axle, and so the sum of the torques will be about the axle. But if you go back to many of the other problems, like the ladder problem, there's no axle. Or the woman doing the push-up problem, there's no axle or axis. So you have to choose, and you could choose this as your axis, you could choose this as your axis, you could choose the center of the woman as the axis, and the same with the ladder. You could choose this, you could choose this, you could choose this, you could actually choose an axis over here, and that maybe doesn't make any sense to you, but I could show you an example where actually if you choose this axis you oftentimes can still solve the problem. So anyway, step 3 is to choose the axis, and so we're going to sum up the torques about the axle, and there's 2 of them, so let's write it out. So remembering that any torque is an R, an F, and a sine theta. So the positive or counterclockwise torque, R2, F2 is what? The tension in the string, which is M2G, and then the angle between that, the R2 and the string is hanging down, and the distance from the center to the string is horizontal, so that's 90 degrees, right? And the negative torque is going to be the R1. The F1 is the M1G. That's the tension in the string from the hanging mass. And notice in this case that the sine of the angle is 45 degrees, right? Here's the rod, here's the mass, and the force is this way, and the R vector from the center is this way. So that's 45-degree angle. And 45 degrees, keep in mind, is the square root of 2 over 2. Or in this case, it's better to write it as 1 over the square root of 2. You can convince yourself that that's the same thing. And so this is all equal to 0. So when you do the algebra, you're going to get R1 equals R2 M2G sine 90, which is 1, divided by the M1G from the other side, 1 over the square root of 2, and of course the G's cancel, and when you simplify all that, you get the final solution. Square root of 2, R2, M2 over M1. Good. Okay, last problem. Another apparatus that you would have set up in lab, if you were in lab, is a post here which goes into the table, and then we have a bracket here with a axle, and then we have a rod with a hole in it that goes here so that this can swing about this axle. And then we stick it over the edge of the table, and there's a hole here where we attach a string and we run it up over a pulley to a hanging mass. And then we, near the end of the rod, we hang another mass. And then in lab we usually try to figure out how much mass do we have to hang here. You can see if this mass is big, it's going to rotate the beam or the bar this way. If this mass is too small, the beam or the bar is going to fall that way. And so in this case we want static equilibrium. We want to figure out how much mass here to support this. And so there's a force at the axle. So this is our diagram, right? Our label diagram, step 1. Step 2, this is our axle and our axis. So here's our free body diagram. And we have M2 acting where the string is. We have M1, M2 acting where it's attached, but we need to know this angle theta because that's going to affect the torque. And then we actually have the weight of the bar or the beam itself acting down here. And so what's not marked in the diagram is this distance from the axis to where the force, which is the weight of the beam itself, which is, even if there was no mass on either end, the beam would fall because it's not torque balanced. Okay, so in this case we are asked to find M2, and so let's go through the general solution for that. So this is another obvious case, but we're going to indicate what our axis is. Our axis is the axle where the rod is pivoting about. And so we're going to calculate the sum of the torques about that point. Everything's going to reference that axle, and they will be equal to 0. And in this case, you can see, I made the diagram pretty small, but you can see that the bar and the mass are going to torque the thing clockwise, so they're negative. So the positive torque is the tension in the string, the distance from the axis to where that acts, that's our R2. And the tension in the string is the M2G, but that's going to be times the sine of the angle. And that will vary according to how we set up the apparatus. In lab, we actually have to measure that. And the two negative torques, so I'm going to just skip the step and just set the positive torque equal to the two negative torques. And the two negative torques are the R of the bar, that's from the axis to the center of mass of the bar, the mass of the bar times G, and that's the sine of 90 degrees, so I'm not going to write it down. And these are the two negative torques, so I'm setting them equal to the positive, so everything is just the magnitude. And the other is the R1, the distance from the axis to M1, and the force M1G, and it's the sine of 90 degrees as well. And so you just need to solve this for M2. And if we divide both sides of the equation by G, as in the other example, the G goes out, and so the M2 is simply the RB MB plus R1 M1 all divided by R2 sine theta. Okay.